to the computer. I am going to begin writing your exam this weekend, so I'm hoping to have a draft of it by Monday or so. I know that we don't have an exam for a couple of weeks now. I think it's what is it, 2 weeks from today? 2 weeks from Monday, I mean, or is it 1 week from Monday? Um, I hope to have it done well in advance so I can review it so that I can, provide any sort of other support that you might need. Okay, so yeah, it's a week from Monday. The way that I write exams and the way that I'm going to write this exam is really no different from how I've written any other exam, and that is by using the learning objectives that I shared with y'all and basically trying to formulate questions from there and saying, okay, well, I brought up this point. How can I ask a question? The way that I always kind of do it is like, what's a very concrete, straightforward question about that? And then what's the question that is like the next level thinking sort of question? And so that basically gives me like 2 questions from each one of those items. And then I'll kind of go through and condense it down. I think the exams are typically going to be about 25 to 35 questions. And those questions are going to be multiple choice or short answer, multiple choice or multiple answer. I think I need to speak a little bit more slowly so then, my thoughts don't get ahead of my words. Um, or my words don't get ahead of my thoughts. There we go. So at any rate, I'll have more to say about the exam this upcoming Monday. And I'll share that with you guys then. In the meantime, though, what we're going to be talking about and going through is glycolysis and the regulation of glycolysis. Now, the regulation of glycolysis is very important to understand. What you've already kind of been exposed to and have a little bit more familiarity and context with is this overall pathway. Now, I do want you to know the names of the enzymes, the full names of the molecules. It's so like this out here, G6P. It's good to know that, but you've got to be able to take that from that contracted form to the full name, glucose 6-phosphate, not just G6P. So I think that that's a worthwhile tool, but make sure that you can kind of interconvert between these two. Then I want you to know the structures and the full names of the molecules and everything like that. Now, with that in mind, we're talking about the regulation of glycolysis. There are already sort of 3 built-in steps that regulate glycolysis. And those steps are your first, third, and 10th steps. So hexokinase, phosphofructokinase, and pyruvate kinase. Why are these the steps that are referred to or recognized as, oh yeah, these are regulatory steps or regulated steps? Well, because of the fact that those are your irreversible enzymes. So it's almost like, I always kind of think about it like a city. If you live in a city where there's, a bunch of two-way roads and then there's like 1 or 2 one-way roads, those 1 or 2 one-way roads are dictating the flow of traffic. So if you're like, oh, I want to go from this point to this point, and there's a one-way road going this way, the opposite direction that you want, well, then you got to find another way around it. So that one-way road going the opposite way that you want is regulating and dictating basically where you can drive and how you can get to different places. Now, that's just a good thing to kind of keep in mind. And that I think that personally is very helpful for me as a good way to think about these 3 steps. So your base level should be, I've got 3 steps that tightly regulate glycolysis: hexokinase, phosphofructokinase, pyruvate kinase. Now, to expand on that, something that's worthwhile to think about, when you have a minute, can you explain? Okay, so I just got a private message about Top Hat. I haven't activated Top Hat yet, so you shouldn't actually be seeing it. I mentioned previously that I would send out an announcement whenever we start to use Top Hat so you can anticipate it. And that's when you won't be able to see it until I make that announcement that, hey, Top Hat's up, you can access it. Here's how you access it. So we will not be using Top Hat today. So I'm hoping that next week we'll begin using that. I'm dealing with some like user issues that I've encountered. Because I took a class and so I was a student, and so I can't be a student and a instructor simultaneously. It's top hat, so I'm sorting that out. And I just haven't had the opportunity to take care of that. So top hat, like I said, you'll get an announcement whenever we actually begin using it. So for the time being, don't worry about it. So you haven't, nobody's lost any points on that or anything like that. Okay, so those are 3 steps. So if we think about hexokinase, one thing that you want to know about hexokinase is, what is the molecule that's input? Glucose. What's the molecule that's output? Glucose 6-phosphate. Okay, so those 2 metabolites are pretty important for the regulation of glycolysis because they regulate hexokinase. Now, this is a big scheme of everything that's taking place with glycolysis. There's a lot to process here, but we're going to break it down bit by bit. Now, if you notice those yellow arrows, those are referencing hexokinase, which I'm going to label it as HK. And then your next yellow arrow is PFK, or phosphofructokinase. And then your last step, going from phosphoenol pyruvate to pyruvate, is your PK, or pyruvate kinase. And I'll actually write this over here. So what I want you to look at whenever you see this is you've got lots of, you've got activators and inhibitors of all of these different enzymes. Some are going to block them, slow down this process, and some are going to speed them up. Now, let's go ahead and simplify it and attack this bit by bit. So what we're first going to look at is regulation of hexokinase. Now, hexokinase is an enzyme that's tightly regulated. It's a one-directional enzyme, or it's favored in one direction. Now, it has a number of different metabolites that regulate its activity. One of those gives basically a negative feedback loop. The product of hexokinase will control whether or not hexokinase is active. So I always kind of think about, and what I think is really helpful when it comes to metabolic pathways and processes like this, is to think about it almost like an assembly line. Each enzyme does one different thing or one thing to this molecule, and then the next enzyme picks it up. So we have this process. Hexokinase, what does it do? It phosphorylates glucose. Okay. Now, in the process of phosphorylating glucose, it makes glucose 6-phosphate. Well, glucose 6-phosphate can go in a couple of different directions. One way that it can go is it could be used for long-term storage in the form of glycogen. We're not going to really get into glycogen storage as a part of this class. You'll get into that in 4385, your metabolism class, but that's one direction that it could go in. Am I going to ask you about glycogen? The most in-depth that I would ask you is, what are the fates of glucose 6-phosphate? Or which of the following are fates of glucose 6-phosphate? One of them is glycogen. One of them is fructose 6-phosphate. Okay. Now, let's imagine that for some reason, both of these steps get knocked out. Those cannot carry out their action. Well, then glucose is going to make glucose 6-phosphate, and at some higher concentration, this glucose 6-phosphate, the product, is basically going to accumulate. It's almost like in an assembly line, well, nothing follows or nothing can utilize that glucose 6-phosphate. So what we have to have is a feedback mechanism so that glucose 6-phosphate can say, hey, there's enough of me, we need to stop, because as we continue, there's way too much of me, so we just have to stop. So that's kind of the, I guess, the explanation or rationale that glucose 6-phosphate regulates hexokinase activity. Now, another metabolite. And so what you can do is say inhibitors of HK. You could say G6P. Glucose G6, that's a backwards P. G6P. glucose 6-phosphate. Another inhibitor would be fructose 6-phosphate. This is a little bit further down on that pathway or further down on that assembly line, but fructose 6-phosphate or F6P also inhibits the activity of hexokinase. Now, this is, however, uniquely reserved for being done in the liver. So in the liver, fructose 6-phosphate will block the activity of hexokinase. So in essence, fructose 6-phosphate will slow down the production of glucose 6-phosphate, thereby it's almost like a safety net. The first safety net, if any one of these processes are disrupted or dysfunctional, well, then you're going to have some sort of feedback, and you're going to give this pathway feedback. Now, glucose 6-phosphate can do that, but in the liver, uniquely in the liver, fructose 6-phosphate can do that. Now, this is where our first layer of complexity rolls in. Another metabolite known as fructose 1-phosphate can block the blocking of hexokinase brought about by fructose 6-phosphate. So it's almost like F1P, fructose 1-phosphate, blocks F6P's blocking. So it blocks the blocking. So is fructose 1,6-phosphate, what's it doing? In effect, it's activating or leading to the production of more fructose 6-phosphate because it blocks the blocking. Now, that's something that I would say that if you plan to study, if you want to go to medical school or something like that, and you want to learn about processes within the body in your metabolism class, that's something that it's very complicated. And what I mean is you learn about inhibitors of inhibitors, and then you learn about inhibitors of inhibitors of inhibitors. So biology and biochemistry is the opposite of any sort of writing class. Like in a writing class, oh, don't use double negatives. Well, a biologist's response to that would be, don't not use double negatives. Because this is just, these metabolites have different impacts on enzymes. And so there are some that are going to directly activate, kind of speeding it up, but then others are going to block how something else blocks. So for hexokinase, we have 3 metabolites. 2 of them, glucose 6-phosphate and fructose 6-phosphate, both inhibit hexokinase activity, or they inhibit the production of glucose 6-phosphate from glucose. Fructose 1-phosphate, the 3rd metabolite, well, it blocks the blocking activity of fructose 6-phosphate. Now, all of this right here, this is all relevant to fructose metabolism. So, if you have a diet that's strictly glucose, then you don't really have to worry about this right here. But if you ingest or if you consume like high fructose corn syrup of some sort, well, then your body is going to be metabolizing fructose. And so you then have to think about how fructose 1-phosphate blocks fructose 6-phosphate. And that's relevant to you because your body processes fructose in a different way than it processes glucose. So I do want you to know about what fructose 1-phosphate does, but we haven't gone into fructose metabolism. That's something that's reserved for your metabolism class. But these 3 molecules, these are important for the conversion of glucose to glucose 6-phosphate. Okay, so that's our first tightly regulated enzyme. Now, our next tightly regulated enzyme and our next irreversible step is phosphofructokinase, or PFK1. Now, PFK1, if you think about what that enzyme does, is it takes fructose 6-phosphate and ATP, or adenosine triphosphate, and makes fructose 1,6-bisphosphate. And actually, let's take a pause. Go ahead and add to the chat a thumbs up for if you think your isomerase and the isomerization from glucose 6-phosphate to fructose 6-phosphate is tightly regulated, or a thumbs down if it is not a tightly regulated step. Thumbs up if it is, thumbs down if it is not. Okay, we got one thumbs down. This is the isomerization. Is that a tightly regulated step? We got two thumbs downs. I bet we can get 3 or 4. 3. Good, good. Nice. Okay, you're absolutely right. This model that I'm showing right here, it's not a tightly regulated step. And we kind of know that because look at this arrow. It's an equilibrium arrow. This is a completely reversible step. So reversible steps, you don't really have to worry about their regulation because those are just going to be, they kind of like feel the winds of change and, oh, we've got too much glucose 6-phosphate, let's make a lot of fructose 6-phosphate. Oh, we got too much fructose 6-phosphate, let's equilibrate that by making more glucose 6-phosphate. So it's just kind of a back and forth like that. Now, fructose or phosphofructokinase, our second irreversible step, our first committed step in glycolysis. Okay, this is an interesting enzyme because it needs ATP, but then it's inhibited by ATP. What gives? That's weird because the thing that it needs, it's also controlled by. So it's almost like I need ATP, but not too much. And that's exactly the rationale. Okay, so the significance of this is that ATP is phosphofructokinase is what's known as an allosteric enzyme. So this is allosterically regulated. What that means and what that relates to is it has a shape that it changes to and from. Now, with that in mind, if there's too high of a concentration of ATP, that's kind of an indication that glycolysis has taken place. You generate ATP through glycolysis. Okay, so it's almost like a check of, hey, we've metabolized enough sugar, metabolized enough glucose, so we don't need any more. So PFK1, slow down, slow your roll. Now, that inhibition can be overcome by adenosine monophosphate, AMP. And to illustrate this, we've got this graph down here. And what this is showing is your activity on your y-axis, your activity of phosphofructokinase, and your fructose 6-phosphate concentration. So we have one metabolite of fructose 6-phosphate, the other being ATP, and we can monitor our production of fructose 1,6-bisphosphate. So I'll bring your attention to this line right here. When the ATP concentration is low, well then we have a lot of activity at right at around 0.5 millimolar fructose 6-phosphate. We're nearing, I'm going to call this 100%. We're nearing 100% activity of our enzyme. So it's basically reaching its top speed or very close to its top speed. Now, what I'd like to draw your attention to is this next line, which relates to this data set, right? Or actually, sorry, jumped ahead of myself. The green line at the bottom, when our ATP concentration is 1 millimolar, which for our intent, let's just call it high ATP. When our ATP concentration is high, what does that mean for our enzyme's activity? Well, it goes from here, it drops down considerably. Okay, so now I want to draw your attention to that middle line. That middle line shows ATP and AMP. Okay, what does that do? When we add AMP, what happens to our activity compared to this green line right here? Our activity goes up. So basically, the inhibitory effect of ATP is offset or overcome by AMP. So that's what we've got going on there. So AMP inhibits the inhibition or offsets any sort of inhibitory effect of ATP. So that's one of the regulators of a regulator. Another metabolite that we have that we need to be thoughtful of is called citrate. Now, for anyone who has taken a cell biology class where you talked about metabolic pathways, and I'm thinking like a functional biology class, you probably talked about glycolysis. Then what's the pathway, add to the chat anyone, what's the pathway that kind of follows glycolysis? And I'll give you a little bit of a hint of where I'm going. It takes place in the mitochondria. It goes by a couple of different names. Citric acid cycle, the Krebs cycle, or the TCA, the tricarboxylic acid. Wonderful, great responses, everyone. Okay, this molecule citrate is found, it's an intermediate, or it's a metabolite within the Krebs cycle. Now, that's important to recognize because this comes after glycolysis, and this molecule can block PFK1. Again, thinking about this as an assembly line, and citrate is way down the assembly line, but it's almost like calling back like, hey, PFK1, stop, we got enough. We've got too much. We haven't really, no, we're still loading the truck up. It's full. Okay, we'd stop. So that's what citrate's doing, much like ATP. So for PFK1, ATP and citrate are both acting in kind of an inhibitory or a negative feedback loop. They're telling PFK, stop, slow down, it's too much. Okay, now this basically gives us two of our tightly regulated steps. The hexokinase, the first step in glycolysis, and our third step, or our second irreversible step, that would be phosphofructokinase. So I like this model because we started with this and it was like, oh my gosh. And we're building it back piece by piece. And this is where we are right now. Now, one thing that's introduced to phosphofructokinase is right here. It's kind of an offshoot. Does anyone want to, or go ahead and add to the chat what you think F26BP stands for? Fructose 2,6-bisphosphate. Perfect. You're absolutely right. Phosphorus was put on the second carbon instead of the first one. 100%. That's exactly what's happening. So there's an enzyme known as PFK. Does anyone want to guess what the name of the enzyme that makes fructose 2,6-bisphosphate is based on what the enzyme that makes fructose 1,6-bisphosphate is? Go ahead and guess the name. And you can use the acronym. PFK1 makes fructose Micaiah, perfect. PFK2, this is one of those instances where I'm like, man, biologists and biochemists, you guys are great. Creativity, not for them. Instead, we say, okay, PFK1 makes fructose 1,6-bisphosphate. We're also finding this other metabolite known as fructose 2,6-bisphosphate. Ooh, we should call that PFK2. There we go. Perfect. So there's what's known as an isozyme, basically. It's called PFK2. It makes fructose 2,6-bisphosphate. That fructose 2,6-bisphosphate is produced with an enzyme that it's almost like I always like to refer to it as a release valve. So when fructose 6-phosphate is accumulating, when there's a bunch of fructose 6-phosphate, well, the primary goal is to get that molecule to go through glycolysis and make fructose 1,6-bisphosphate. But there's a release valve, and that is the enzyme PFK2. So PFK1 and PFK2 are working kind of side by side. It's almost like PFK2 is, when needed, it can help out, but it's not always needed. It's needed whenever there's a high concentration of fructose 6-phosphate. And then whenever it's needed, it's called upon and it does its action. And that molecule, fructose 2,6-bisphosphate, activates PFK1. So it's a release valve because it prevents the accumulation of ATP, but that molecule also activates PFK1. Now, what's also taking place is that there are, we'll not do this. Fructose 2,6-bisphosphate is a regulatory compound that stimulates and activates PFK1. So PFK2, what's unique about PFK2 compared to PFK1 is that, sure, it makes fructose 2,6-bisphosphate. Great. But what this enzyme also does, I always like to draw a visual for it. This is my enzyme. So here's our just a linear molecule, just for the sake of simplicity. Half of it has the ability to, or half of it has like kinase activity. It has the ability to produce F26BP. The other is able to, so I'm going to say the kinase can make. So half of the enzyme, half of PFK2 can make fructose 2,6-bisphosphate. The other half can make F6P from F26BP. So it does the reverse reaction. This is a stark contrast to PFK1 because we know that PFK1, all that it can do is go in the forward direction. So PFK2 is kind of dynamic. It can make fructose 2,6-bisphosphate when there's a bunch of that fructose 6-phosphate, but then it can also remake fructose 6-phosphate whenever it needs to. So whenever that concentration of fructose 6-phosphate goes down, then PFK2 gets activated and says, all right, cool, I'm going to make it. Now that protein, so these are the two functions, PFK2 and F26BPase, or bisphosphatase. Write that out, bisphosphatase. So this enzyme is on one polypeptide. These two functions are on one polypeptide. So one enzyme, one protein does these two opposite directions, or these two opposite things. These two enzymes are regulated by metabolites and by hormones. Now, hormones are going to vary, their distribution are going to vary within tissues. Then last but not least, this enzyme is not present in bacteria. So we've got this little variable that we've added in. Now, hormones, this subsection right here, that's our first enzyme that we've talked about as being regulated by hormones. I haven't mentioned specifically, and I haven't mentioned applying any of these hormones, so we'll get to that in just a little bit. But that's essentially what we have going on there. That's the new wrinkle that we've added. Now, our last enzyme, our last irreversible step is pyruvate kinase. Pyruvate kinase takes phosphoenolpyruvate, ADP, and makes our last ATP. So remember, this is our last step in the payoff. So this is the last step that makes ATP that we needed to produce. Now, pyruvate kinase is an enzyme that's activated by a couple of different things. Activated by AMP. Okay, what you'll learn as you proceed through your life science or biochemistry classes is that AMP is pretty commonly an activator. Does anyone add to the chat, think of an instance where you've heard about AMP or something similar to AMP? And I'll give you a little bit of a spoiler. there's a letter in front of AMP that's kind of maybe given a little bit more familiarity to you. Cyclic AMP, CAMP, perfect. So that's a molecule that gets cyclized, and cyclic AMP and AMP are pretty regularly activators of, or regulators of different enzymes. Now, pyruvate kinase is also regulated by fructose 1,6-bisphosphate. That's interesting. Let's jog back for a second. Where is fructose 1,6-bisphosphate? Well, it is right here. So it's upstream of pyruvate kinase. So essentially this metabolite, if it accumulates, then what it says is basically, hey, pyruvate kinase, you need to get off your duff and you need to make more pyruvate because there's a ton of me here. I need you to get moving so that I can be processed and I can be made into pyruvate. I always like to anthropomorphize enzymes and give them personalities and metabolites. But that fructose 1,6-bisphosphate is kind of like, it's like, come on, pyruvate kinase, let's get the lead out, let's move. Now, inhibitors of pyruvate kinase are ATP, adenosine triphosphate, acetyl-CoA, and the amino acid alanine. Okay, so these two are feedback loops because, you know, ATP is a product of pyruvate kinase. So it's almost like when the concentration of ATP gets really high, that's almost a way of saying to the enzymes that use ATP or make ATP, like, hey, we're trying to generate ATP. We've gotten to this concentration. We've got enough ATP so we can stop. That's essentially what it's communicating. Acetyl-CoA. Now that's a molecule that we haven't talked about, but down here in the mitochondria, in the powerhouse of the cell, that's where we've got this, where we have the citric acid cycle, the tricarboxylic acid cycle, the Krebs cycle. I use those three terms because that's what it's commonly referred to as. Those three terms are interchangeable. Acetyl-CoA is a major metabolite in the citric acid cycle. So it's basically a metabolite that follows the action of pyruvate kinase. So if acetyl-CoA's concentration is super high, then it's going to go back to pyruvate kinase and it's going to act similar to ATP. And it's going to say, hey, we need to stop because there's enough of me. So until we start moving and breaking down more of this acetyl-CoA, we need to go ahead and stop. Now, those are our small molecules that regulate pyruvate kinase. Pyruvate kinase in the liver is also regulated by different hormones. For example, it can be inhibited by epinephrine as well as glucagon. It can be activated by insulin. So just to provide a little bit of context, glucagon is the hormone that your body produces whenever you have low blood sugar. It's basically a hormone that says, hey, the blood sugar level is low, which is why, you know, in the liver, this is this is where it acts in the liver. So it says like, hey, we need to stop using glucose. Stop using glucose. Because right now it is at a dangerously low level. Now, insulin works in the opposite direction as glucagon. What insulin does is it says, hey, we have basically too much sugar. We have an excess of sugar. So we need to start using glucose. So these two hormones work in opposite directions as one another. Now, in terms of what they regulate, I think that it's helpful to think, okay, well, why would you want to inhibit pyruvate kinase? Well, pyruvate kinase is our final step in glucose metabolism and glucose breakdown. Well, you want to stop that because if you continue doing it, then any more glucose that is available will be siphoned through this pathway. But if you stop pyruvate kinase, then that glucose basically gets stuck as glucose and can go back into the bloodstream. So it's almost like you can replenish the bloodstream glucose by blocking pyruvate kinase. If the blood glucose level is super high, well, then insulin will act to activate an enzyme like pyruvate kinase and says, hey, we have so much glucose, we need to use it. Now, are these the only actions of glucagon and insulin? No. Glucagon and insulin work on tons of other proteins, whether they're transport proteins that make sure that glucose gets into the cell and stays in the cell, or some of those hormones upstream. But for right now, what I want you to know is that insulin and glucagon, and epinephrine for that matter, they act in kind of opposite directions. Epinephrine and glucagon inhibit pyruvate kinase, and basically they are wanting to say stop using glucose. Whereas insulin says, hey, we've got an excess of glucose, let's use it. So essentially, this is what we've put together. We've worked through and we've kind of built this model up where we started with basically our first enzyme being hexokinase, which I need to add one detail here. In the liver, we don't have hexokinase. Add to the chat what is the name of the enzyme that catalyzes this reaction in the liver. So catalyzes the production of glucose 6-phosphate from glucose. What is the name of the enzyme in the liver that does that? Hexokinase does it in basically every other cell type. Glucokinase, perfect. So I'm sorry for misspeaking earlier. I need to make a correction here. Fructose 6-phosphate is not an inhibitor of hexokinase, but instead it is an inhibitor of glucokinase. So inhibitor of GK or glucokinase. That is F6P. Fructose 6-phosphate is an inhibitor of that. So we have regulation of that first step. And sometimes I'll refer to enzymes based on the reaction that's being catalyzed. I'll say something like the phosphorylation of glucose to make glucose 6-phosphate. Well, glucose 6-phosphate, that's our first irreversible step. Then what we're interested in is PFK1, which is our first committed step. Now, PFK2 also assists in that, kind of working as a release valve to make fructose 2,6-bisphosphate. And then citrate and ATP are regulators of PFK1, whereas PFK2, that serves to produce fructose 2,6-bisphosphate, which activates PFK1. Now, that leads to the production of fructose 1,6-bisphosphate, and all of the steps from fructose 1,6-bisphosphate to phosphoenol pyruvate are completely reversible. That's a two-way road there, and it's all kind of responsive to concentrations. Oh, there's a high concentration of fructose 1,6-bisphosphate. Great. Let's go ahead and split that molecule into our aldose and our ketose. We'll continue on through there. We've got to isomerize it. We do a dehydrogenase or a oxidoreductase reaction. Then finally, we get to phosphoenol pyruvate, where we're making pyruvate by removing a phosphate group from there to make our pyruvate. And that's going to be regulated. It's going to be activated by AMP and fructose 1,6-bisphosphate. And it's going to be inhibited by ATP, acetyl-CoA, and the amino acid alanine. I'm not going to go into the alanine regulation because that's something that you'll get and discuss in your metabolism class. But that alanine is going to inhibit the pyruvate kinase. Like I said, though, I'm not going to ask any questions about alanine regulation, so I'm going to scribble that out. Instead, what I want you to focus on is ATP and acetyl-CoA. What are activators of pyruvate kinase? AMP and fructose 1,6-bisphosphate. However, hormones also regulate these. Pyruvate kinase is going to be inhibited by glucagon and epinephrine, which are basically hormones that communicate, hey, blood sugar is low. Let's go ahead and stop using sugar because we need to kind of replenish it. And then pyruvate kinase is activated by insulin. Let's start using more sugar because we've got an abundance or an excess of it. That brings us back to what we kind of constructed. This to me is something that is best kind of consumed in piecemeal. So I think that it's productive to think about it as, okay, what is this reaction? What are the regulators of it? What activates it? Does anything inhibit it? And then you get to that next level where it's like, okay, this inhibits it, but what inhibits the inhibition? This inhibits the inhibition. For example, AMP inhibits the inhibition of ATP. So you could almost look at that as AMP activates PFK1. Okay, well, that's where I wanted to stop today. Again, regulation, we're focused on 3 enzymes. So if you think about glycolysis and the regulation of glycolysis, I think that it's helpful to kind of narrow in and focus in on these steps, because then you're not trying to process 10 steps at once. The better that you know these 3 steps, the better that you know the entire pathway. In addition to that, when it comes to your exam, and this is kind of a theme for me, whenever I ask questions on exams, and I think that it's a more worthwhile time for me to ask questions about interesting things. So, ask about I'm more likely to ask you about pyruvate kinase or PFK1 than I am to ask you about an isomerase, which is, why? Well, because an isomerase just isomerizes. It just takes glucose 6-phosphate, makes fructose 6-phosphate. For all intents and purposes, that's not super interesting. And I say this as a theme because as we go on to learn about amino acid structures, I'm going to spend more time talking about amino acid structures than I am about, some amino acid structures than others, because some of them are interesting because they change based on pH, or they form, covalent bonds. Others are uninteresting because they're just hydrophobic. They're nonpolar. It's just, that's all there is to it. At any rate, I hope that you have a great day. I hope you have a great weekend. And like myself, just forget that the Bobcats played a football game yesterday. It was a good game. They were very close, but it wasn't in the cards today. Saturday, though, I think. Next Saturday. All right, everyone. Have a great weekend. And yeah, have a great day. Thanks for coming to class, everyone.